Welcome to section 5.2. In this section, we are going to define something very important to us and is going to be at play throughout the rest of your calculus career. It's called the definite integral, okay? And it's where we now formalize the idea of, well, calculating the area under a curve, but becomes more abstract than that. So how do we find the actual area? We can certainly approximate it using Riemann sums, we're going to call them, but how is it that we're able to do this? Okay, so the laundry list of what we cover is rather lengthy, so I'm going to have to break this section up into hopefully 3 rather short segments, videos. We'll see. Okay, so the idea is the following. If you were to take a curve, and basically do what we've been doing, which is, I've got a function f, and I'm interested in the area, let's say for now, from A to B under this curve. And of course, what we have been doing is we have been breaking this up into subintervals. This part we're going to formalize a little more. And then what we have been doing is basically approximating the area under the curve by adding up a bunch of these subinterval rectangular areas, as we've been talking before. Okay, so what that looks like in summation notation, which needs to be introduced, is the following. It looks like, well, the area is approximately equal to the sum of every one of these n subinterval. Let's say there's n, there's 12, there's 20, and you're basically adding up those areas of the rectangles, the rectangular areas. Okay, so the idea up here, the more subintervals you use, the better the estimate, is true, because if you're going to make it a little more fine as you're coming up with your approximation of this guy, and I should have made those wider, but now we're going to break it up into tiny little subintervals and smaller still, and each one is just really, really thin. And that means correspondingly each one of their areas is closer to the actual area under the curve. So, hey, the more subintervals you use, the better the estimate is the idea. And so that is the genesis and actually the birth of what we call the definite integral, and it's defined on page 378 for you to look up, and here it is. It gives us a new notation. Let's look at the notation. I'll write it down here. So the definite integral, as opposed to, in another section, the indefinite integral, you'll explain that when we get there. The definite integral is this thing. This notation, that squiggle there looks like a fanciful S, right? This guy right there. It's an integral symbol, I think. I'm sure it has a name. Okay, and it's like a fancy S. And likewise, over here, the sigma was Greek for S, except this one over here is more refined. We're going to take the sum of these areas, but we're going to make the division of the subintervals, of the interval into subintervals, finer and finer and finer. And then in here, the notation continues. It says it is f of x dx. And we've seen dx before. We call that a differential in a previous chapter on differentiation. But here's the definition. If this limit exists, it's equal to the lim as n goes to infinity. What does n stand for? N subintervals. That's what it stands for. N subintervals. So you can dream up a silly example like over here you have like n is equal to 12. Then over here n is equal to 52 or something like that. Just making numbers up. But the more subintervals you use, the better the approximation, and hence the idea of letting n, the number of subintervals, get larger and larger and larger towards infinity. And here's the formula. It is f of x sub I star, or splat, or whatever you want to call it, times delta x. So let's talk about this guy. This is where we want to spend some time, okay? All right, so first of all, the numbers here, I bet you recognize them, the A and the B. Well, that's the start and the stop of your subinterval. And these are called the limits of integration. You know how I've been saying anti-derive, but sometimes I slip by saying integrate, integrate? The word we're going to use from now on, we hardly ever say anti-derive from now on. We'll say, what's the integral? Integrate this, integrate that, okay? The function inside here actually has a name. We don't use it often, but it's the integrand. It's the guy you are integrating, okay, the function that you are interested in. And then the dx here is basically your differential. And it really says it's a differential. A lot of this might be symbolic, but what it really says is we're integrating with respect to x. Okay, we talk that way too. So I'll say that integrating with respect to x will be a thing we say later on down the road once we learn the easy ways of doing things. Okay, so they're saying this guy, this symbol that we just tore apart with our names, represents this concept of taking the limit at infinity. Okay, that's the definite integral. That's what we're talking about. We have a theorem that is at the top. It says if f is continuous, then it's integrable. I said that was theorem 3 up there, but this is theorem 4. Oh well, it's a theorem. If f is continuous, or at most finitely piecewise discontinuous, that is, it might have a vertical asymptote or whatever now and again, then it is what we say integrable. What that means is that this limit actually exists. And now we're going to get into a little more of the mechanics of it. So let's draw another picture of this thing. Okay, so we got this going. This is A, this is B. And again, your function's floating through space. And what we're going to do is break it up into pieces again. But we're going to break it up into n sub-intervals of equal length. Okay? And so that means you go here and you take out your Ginsu knife or whatever, and you make sure, mathematically speaking, what we do is we just say that all those subintervals have the same length. Okay, so then my question to you is, algebra lovers, what is the length of each of those subintervals? Okay, well, what you do is you take the length of the interval and divide it by n, however many you want. And so what you would say, what happens then is you go, well, the length of the interval is the big number minus the small number, and then divide by the number of subintervals you use. And by the way, folks, that's delta x. So imagine marching your way, okay, starting at A and then jumping that far, which means, by the way, this guy is A plus delta x, right? Okay. And then you go another step, and then this right endpoint, if you will, is A plus delta x, but then another one, so twice delta x, like so. And so on, and so on, and so on. So if we say, if we let the choice of x sub I star, now here's the thing, the choice of x sub I star, what are you talking about? In any subintervals, let's look at the first one. I'll go black on this one, okay? You have a choice in this interval of which x to use. You can use the left endpoint, the right endpoint, the midpoint. What do you mean use? You remember we plugged in, if I use the right endpoint, it looks like this. We plugged into the function the right endpoint to find the height of the rectangle. But we didn't have to do that. We can go left endpoint, we can go right, or even midpoint. So x sub I star is your choice, basically your choice of x in the ith subinterval. And what do you do with that guy? Well, you plug it into the function and it tells you how high the rectangle is. Now, if we let x sub I star equal the right endpoint, right? Let's do that. And the book says too, might as well just use the right endpoint for what we're about to do in section 2. Okay, if we let x equal the right endpoint, okay, then that means x sub I star is equal to, watch out for this, in the first one, if I is equal to 1, we have a plus delta x times 1. If I is equal to 2, we have a plus 2 times delta x. If I is equal to 3, we have a plus 3 times delta. What the heck are you talking about? Remember over here? You're leapfrogging, going up delta x, up delta x, up delta x, up delta x. And so what we have is the following. We have x sub I star is a plus delta x times I. Okay? So if I is 1, you just jump over once. It's the right endpoint of the first subinterval. If I is 2, you jump over twice. It's the right endpoint of the second subinterval. On down the line until finally I is equal to n and you're at b. Okay? You're at b. Because I would be n and there you have it. So that formula, that's where you're getting this formula here, and that's going to help us later on our third video. But we've got a ways to go before that. I wanted to point out something, though. One last thing. We're going to look at 2 properties after this, what I'm going to show you, and then this video is going to end. Then I'm going to do a video on the rest of the properties, and then I'm going to give you one example, another example. I did one in class on Zoom, but we'll do another one. Okay, so now bear in mind, okay, that all the time I've been having f up in the first quadrant. But who says f is in the first quadrant? I mean, the function of f could be negative, it could be positive. In fact, I think I'll give you an even more generic picture, and I'll draw a picture of an f that does something like, well, you know, something like that. This is our f, okay? I don't like that f, so let's get rid of that and do better, okay? So it could be something like, it could be, you know, something like dropping down like this and cruising like that. Okay. Let's say that you decide to integrate, say, from A to B here. Okay. Well, that truly would be the area under the curve, wouldn't it then? You know, all your rectangles would be lining up nicely like that. Okay. But what if someone extended the integration to, say, maybe make this A and this B? Or maybe even just this B? Okay. It's arbitrary what your limits are. But here's what I wanted to show you. Okay. In this region, your function values, f of x sub I star, are positive. So that when you're doing your sum, okay, you're doing summation f of x sub I star times delta x, okay. Remember delta x is the length of each subinterval, like so. When you're doing that stuff, okay, then all your function values are positive, the delta x is positive, so you're going to get a positive sum. But if you're in this region, f of x sub I star over here somewhere, is going to be negative. It's going to be less than 0. In this region, f of x sub I star is positive. Over here, it's negative. So we get this idea of a negative quote-unquote area. So you have a negative, well, I'll say it is negative for sure. The quote-unquote is area. You go to geometry class and say, I got a negative area, they'll think you're crazy. So what happens in this case? If I integrate from A to B, I get a so-called negative area here plus a positive area here, and they're going to counteract each other. And your net, and we use that word in this class, the net result is either positive or negative, depending. And sometimes integrals are 0. I'll give you, for instance, if we took, say, and we're going to do this later, if we took the sine wave and we integrated from 0 to pi, and we said, what's the integral from 2 pi of the sine wave, which that's a little far out for us, and maybe in a couple sections it'll be an easy one, and it will be. Well, what's the integral of this? By looking at this picture, this is a positive, but it's absolutely symmetric with this guy, negative. The net result you can guess is 0, because you have an identical positive and a negative area canceling each other out. Okay? Fascinating stuff. This could happen. In this picture over here, you got some positive piece over here. Over here, it's a negative piece. It all depends on where you start and stop your integration. Next semester, we'll talk about a function that has an asymptote. What do you do if you're integrated from here to here and he's doing this kind of number? Well, next semester we'll hold off. It ends up being an improper integral that we need to deal with next time. Okay, so let's do a couple of properties here. This one says, and I said this in our language, flip the limits of integration. What it does is it changes the sign of your integral. And the question is, why? Okay, and the answer is found really in the definition of delta x being b minus a over n. Okay, so if you got f cruising through space like this, a to b, and you're divvying up like this from a to b, right? Then your formula b minus a is greater than 0. But if you decide to integrate the opposite direction, and the definition is still, b minus a over n, that is to say right here, then all of a sudden b minus a over n is negative. So you have quote-unquote negative lengths of subintervals. So you change the sign of b minus a over n if you integrate from b backward to a. And that makes sense, doesn't it? That you end up with the negative of the integral you're working on. You have to think about that one. Okay. There's another one here I wanted to talk about. If you want to pause it and look at it, go ahead and draw your own pictures. This one's easier to see than that one. It says basically, look at this. If the upper and lower limits of an integral are the same, then the integral is 0. And you can almost figure that one out, because here's f doing its thing, and you decide, I'm going to integrate from a to a. What kind of area is that? What is b minus a over n? It's 0, 0, 0. So that makes a lot of sense that if you integrate from 5 to 5, some funky thing like the natural log of x dx, it's going to be 0. I don't care what you call it. Whatever function's in there, it's 0 if it's a continuous function, that is. So those are a couple of the properties. There's a few more to talk about on the next video, okay? So we're getting started. Stay tuned for the next one.